Small signal stability analysis of the interactions between voltage source converters and DC current flow controllers. Section 3. Interactions between CFC and VSC. In Section 3, the test system is introduced. Then dynamic analysis of the integrated AC-DC system without and with CFC is studied to investigate the impacts of the incorporation of CFC. Finally, the interactions between CFC and VSC are investigated. A test system. Figure 6 shows the test system topology of the CFC integrated AC-DC system, which was modified based on the Kunder S4 generator 2-area system, proposed in reference 15, where parameters can be found. The test system consists of 2 areas connected by a weak tie, 220 km transmission line, and a 3-terminal AC-DC network. The pole-to-pole DC voltage is 120 kV. The CFC is integrated into the DC network to control DC currents. VSC2 is operating in VDC-VAC control, controlling the DC voltage in the AC voltage. VSC1 and VSC3 are operating in PVAC control, controlling the active power through converters in the AC voltages. The 2-line CFC is installed at the DC side of VSC1 to control current flow from VSC1 to VSC3 and VSC1 to VSC2. The parameters of the DC network and CFC are shown in Table 1. The control parameters for control system of CFC are from reference 25, and the control parameters for control system of VSC is based on the approach proposed in reference 9. B. Dynamic analysis of the integrated system with CFC. In order to study the impacts of the incorporation of CFC on small signal stability of the integrated AC-DC system, eigenvalue analysis is carried out for the system without CFC and the system with CFC. The small signal stability of the AC-DC system shown in Figure 6 is to be assessed by modal analysis. The complete state space matrix of the integrated system without CFC has a dimension of 52-52 and complete state space matrix A of CFC integrated system has a dimension of 55-55. The calculated eigenvalues of system with CFC are given in Table 2. There are 52 eigenvalues for the system without CFC and 55 eigenvalues for the system with CFC. The additional 3 states are resulting from the CFC capacitor and 2 integral controllers of CFC, delta UC, delta Y1, delta Y2. From Table 2, it can be seen that all 55 eigenvalues have non-positive real part. This indicates a stable operating condition around the operating point. There are 2 zero eigenvalues lambda 48-49, as there is no infinite bus bar in the testing system. 1 zero eigenvalue arises from a redundancy in synchronous generator angle. The second zero eigenvalue results from that the generator torque is independent of machine speed deviations, and this is caused by the fact that mechanical damping is neglected and governor action is not represented. The eigenvalues lambda 11-12, lambda 14-15, lambda 18-19 to lambda 24-25, lambda 29-30, and lambda 35-36 are related to the dominant state variables of synchronous generators, according to their participation factors. The damping of these modes is mainly affected by synchronous generator settings, associated exciter settings, and corresponding PSS parameters. The incorporation of CFC has no significant impacts on these synchronous generator-related eigenvalues. The participation matrix also indicates that controller of VSC3 has dominant influence on lambda 39-40. Based on participation matrix, it should be noted that state variables I12 and I13 of the DC network have dominant influence on the oscillation modes of lambda 5-6 and lambda 7-8, while auxiliary state variable Y1 of CFC controller dominantly influences lambda 31-32. The results of modal analysis show that the incorporation of CFC and its controller parameters affect the small signal stability of multi-machine AC-DC system. Figure 7 shows a plot of eigenvalues of the system without CFC, while Figure 8 shows a plot of eigenvalues of the system with CFC. The dominant states in the associated pairs of eigenvalues are highlighted in Figure 7b for the system without CFC and in Figure 8b for the system with CFC. Compared to the system without CFC as shown in Figure 7b, it can be seen that the system with CFC, as shown in Figure 8b, has 3 additional conjugate pairs of eigenvalues, which are dominated by state variables of DC branch currents, I12, I13, and CFC integral controller auxiliary state Y2. Also, the system with CFC has very slight impacts on the generator-related eigenvalues as there are no significant changes in the placements of those eigenvalues. However, the system with CFC leads to the changing of VSC controller-related eigenvalues from the pure negative real values to the conjugate pair of eigenvalues with negative real part, as highlighted by VSC 2x3 in Figure 8b. This change results in VSC controller-related system oscillations for the system with CFC. This is due to the potential interactions between CFC and adjacent VSC. From Figure 8, the critical modes which have major impacts on small signal performance of the system are associated with DC-CFC auxiliary state Y2, VSC2 auxiliary state X3, and the angle and rotating speed of synchronous generator 1. The AC-DC test system as shown in Figure 6 has been established in RSEAD to validate the results of modal analysis. The power flow data, AC voltages, and impedance values are based on the 4-generator 2-area benchmark system model in reference 15, while the parameters of the DC network and CFC are shown in Table 1. The max power loss of CFC, considering conduction and switching loss, is 1.6 megawatts, 1.6% of the system power rating, which is much lower than losses due to the resistances in the DC lines. 1. Simulations under small disturbances. Figure 9 shows the dynamic behavior of the system, controlled DC branch current I12, and voltage across CFC bridge capacitor UC, in response to a step reference change applied to CFC. I12 ref changes from 0.55 kA to 0.50 kA at 0.1 seconds. It can be seen from Figure 9 that the controlled current of DC branch 12 decreases from 0.55 kA to 0.50 kA. The voltage of DC capacitor returns to its reference value after the small disturbance. Stable dynamic performance can be seen from the simulation results, which is in line with the modal analysis results. 2. Simulations under large disturbances, AC system fault. In this subsection, a large disturbance is applied to test the system stability under large disturbances. A 10 ohm single line to ground fault is simulated at the point of common coupling of VSC3, primary side of coupling transformer, at 0.3 seconds, lasting for 7 cycles, 116 milliseconds. Figure 10 shows system dynamics of MTDC system, including active power transfer of VSC1 and VSC3. These two converters are in PVAC control, and current of DC branch 12. The system recovers to steady state in a short period of time after the fault is cleared. It demonstrates that the system can endure large AC disturbance and recover quickly. 3. Simulations under large disturbances, DC cable fault. For the testing of large disturbance at DC side, a 25 ohms line to ground DC cable fault is simulated at DC side of VSC3 at 0.3 seconds, lasting for 7 cycles, 116 milliseconds. Figure 11 shows the system dynamic response results of controlled DC branch current I12 and bridge capacitor voltage UC. The system recovers to its former state after the fault is cleared. The simulation results show that the system can endure DC side large disturbances. See impacts of control parameters of CFC on VSC. The effects of the control parameters of CFC on VSC are studied in this section. It has been found from modal analysis that different values of the CFC controller gains KPC1, KIC1, KPC2, and KIC2 can affect dynamic stability of the integrated AC-DC system, especially on those VSC state variable related modes. The stable-unstable setting ranges of KPC1, KIC1, KPC2, and KIC2 are obtained by the procedure shown in Figure 12. For the given test system described in Section 2, the stable-unstable setting ranges of KPC2 is listed as shown in Table 3, which is used as an example to investigate system dynamic stability when CFC controller gains are changed. Table 4 lists 3 different values of KPC2, KPC2 equals 0.01, 0.1, and 1, and relevant modes. The corresponding values of lambda 3132 are 0.16 plus minus J1.07, 0.09 plus minus J1.08, and minus 0.55 plus minus J0.93. It can be found that the system is stable only when KPC2 is greater than or equal to 1. The time domain simulations in Figure 13 are in line with the results shown in Table 4. When a small change of the reference is applied, I12 ref changes from 0.55 kA to 0.50 kA at 0.5 seconds. Stable system dynamics can be achieved only when kpc2 equals 1. Unstable oscillations are observed for kpc2 equals 0.1 and kpc2 equals 0.01. It can also be seen that large kpc2 decreases the oscillation frequency and the settling time. The value of kpc2 has significant effects on state variables I12 and Y2. These results demonstrate that the control parameters of CFC may cause instability of the system if they are not carefully tuned. As shown in Figure 14, eigenvalue trajectory study is used to plot the movements of critical conjugate pairs so that the impacts of changing control parameters of CFC on VSC-related modes can be analyzed. In Figure 14, the control gain kpc2 varies from 0 pu to 1000 pu, while the values of other control gains remain same. The purple arrows indicate the movements of conjugate pairs resulting from this variation of kpc2. As shown in Figure 14a, the imaginary parts of CFC-related conjugate pairs, I12 and I13, decreases kpc2 increases, which indicates greater damping ratios of CFC-related states. As shown in Figure 14a, two new VSC-related conjugate pairs VDC2 and VDC1 highlighted in blue, emerges kpc2 increases. The movements of VSC-related pairs, VDC2, VDC1, and VSC-X32, as shown in Figure 14a-b, clearly present the impacts of CFC on VSC. The two conjugate pairs of VDC2 and VDC1 move towards left half of S-plane, which indicates larger damping ratios of VSC-related states, VDC2 and VDC1. The conjugate pairs of VSC-X32 move towards right-hand side, indicating less damping ratios of VSC-X32. As shown in Figure 14a-b, there are no significant movements of generator-related poles, which indicate CFC has no significant impacts on synchronous machine-related states. Based on eigenvalue trajectory studies of CFC control gains, it can be summarized that the variation of CFC controller can affect dynamic stability of CFC and VSC-related modes. These impacts of CFC on VSC can result in different damping characteristics of VSC-related states as CFC controller changes. As listed in Table 5, 3 cases of different CFC control parameters are designed based on eigenvalue trajectories of various CFC control gains to investigate their effects on the VSC controller-related modes. Case 1. The control system of CFC is disabled as the base case to represent system without CFC control system. Case 2. The gains of CFC control system are set the same as those in reference 25, kpc1 equals 1, kic1 equals 1, kpc2 equals 1, kic2 equals 1, to represent the normal settings. The oscillations of VSC2 controller-related modes are seen from Table 5. The AC/DC system is stable for the first 2 cases. Case 3. The gains of CFC control system are changed, kpc1 equals 0.01, kic1 equals 1000, kpc2 equals 1, kic2 equals 1000, to represent extreme or possible fault conditions of CFC control system. One conjugate pair of eigenvalues with positive real part is seen, which indicates small signal instability. Figure 15 shows time domain simulation results of 3 cases. As shown in Figure 15, a small perturbation, DC branch current reference I12 changes from 0.55 kA to 0.5 kA is applied to CFC at 0.15 seconds. For Case 1, no significant change of VSC2 auxiliary state variable X3 is observed because the CFC control system is disabled. For Case 2, a small increase of X3 at 0.2 seconds can be seen. Then the value of X3 recovers to its pre-disturbance level after a period time of oscillations. For Case 3, large unstable oscillations are seen. Simulation results are in line with the modal analysis results in Table 5 and illustrate that the CFC control system can affect dynamic performance of VSC converter controller. This effect can be severe and cause instability to the AC/DC system for extreme DC-CFC operating conditions. The possible reason of these interactions between CFC control system and VSC controller can be the dynamical changing of the interfacing variables that relate CFC controlled variable and adjacent VSC controlled variable. For instance, CFC controls DC branch current I12, and VSC converter 2 controls DC voltage of VSC2 VDC2. And the relation between these two controlled state variables is given in equation 5a. The impacts of control parameters of VSC on CFC. The effects of the control parameters of VSC on CFC are studied in this section. Eigenvalue trajectory study is implemented to investigate potential impacts of different values of the control gains of VSC controller, KPDC, KIDC, KPID, KIID, KPAC, KIAC, KPIQ and KIIQ, on system dynamic stability of the integrated AC-DC system, especially on CFC state variable-related critical modes. The stable setting ranges of the control parameters of VSC controller are obtained using the approaches presented in reference 9. As eigenvalue trajectories shown in Figure 16, the movements of critical conjugate pairs present the impacts of changing control parameters of VSC on CFC-related modes. In Figure 16, the control gain KIDC varies from 0 pu to 1000 pu, while the values of other gains of VSC remain same. The purple arrows indicate the movements of conjugate pairs resulting from this variation of KIDC. As shown in Figure 16c, 3 new generator-related conjugate pairs, highlighted in both green and purple arrow, emerge as KIDC increases. As shown in Figure 16bd, the imaginary parts of generator-related conjugate pairs increase as KIDC increases. This indicates greater damping ratios of corresponding generator-related states. The movements of generator-related pairs are less than those of CFC-related and VSC-related pairs as shown in Figure 16b and d. The new VSC X32 related conjugate pair emerges as KIDC increases, as shown in Figure 16d. The VSC related conjugate pairs move towards left half of S-plane as KIDC increases, which indicates greater damping ratios of VSC related states. It should be noted that positive eigenvalues are seen in Figure 16d. This is due to the variation range of KIDC covers all stable and part of unstable operating range. As shown in Figure 16b and d, the movements of CFC-related pairs, I12, I13, and Xi2, clearly present the impacts of VSC on CFC. The two conjugate pairs of I12 and I13 move towards right half of S-plane, which indicates reduced damping ratios of CFC-related states I12 and I13. The conjugate pair of Xi2 moves towards left-hand side, indicating increased damping ratios of Xi2. Based on eigenvalue trajectory studies of VSC control gains, it can be summarized that the variation of VSC controller can affect dynamic stability of synchronous generators, VSC, and CFC-related modes. These impacts of VSC on CFC can result in different damping characteristics of CFC-related states as VSC controller changes. And improper VSC controller tuning may cause instability to the integrated system. As listed in Table 6, 2 cases with different VSC control parameters are designed based on eigenvalue trajectory studies of various VSC control gains to investigate their effects on the CFC-related system stability modes. Case 4. Control parameters, value of the gains of proportional and integral controllers of VSC2 are set to normal operating values, KPDC equals 7.52, KPAC equals -10, KPID equals 0.3, KPIQ equals 0.3, KIDC equals 1, KIAC equals -1, KIID equals 1, KIIQ equals 1. The system is stable. Case 5. Controller of VSC2 is set with abnormal values, KPDC equals 7.52, KPAC equals -10, KPID equals 0.3, KPIQ equals 0.3, KIDC equals 10, KIAC equals -1000, KIID equals 1, KIIQ equals 1, which represents extreme or faulty VSC operating condition. One conjugate pair of eigenvalues with positive real part can be seen, which indicates small signal instability. Figure 17 shows time domain simulation results for the effects of control parameters of VSC2 on dynamic performance of CFC. As shown in Figure 17, a small perturbation, DC branch current reference I12 changes from 0.5 kA to 0.55 kA is applied to CFC at 0.3 seconds. For Case 4, I12 quickly increases to 0.55 kA in response to the change of reference. For Case 5, large oscillations can be observed, which indicates instability of CFC integrated DC network. Simulation results demonstrate that the VSC controller can affect the dynamic performance of CFC. and this effect can be severe and cause instability of the CFC integrated DC network for extreme VSC operating conditions.